So I'm not going to lie to you. This problem is a bit of a doozy. So this is a polyatomic ion, sulfate ion to be exact. And what I want you to do is I want you to give me a Lewis structure. Now that seems pretty straightforward. Leave yourself some room, okay? Just make sure that you leave yourself some room. Okay, so SO4 2 minus. Let's write a Lewis structure and just kind of see where we get. So I've got 1 sulfur, which is 1 times 6, which is 6. Got 4 oxygens. 4 times 6 is 24. I've got 2 times a negative charge. That's 2 times 1. That's 2. 32 electrons total. Okay. So I'm going to draw my first one. And I'm going to connect all with single bonds. Okay. And then just for the sake of this problem, instead of doing this, because it's kind of hard on my computer to do that, I'm going to say that is equal to a line. So I'm just going to do this. Now, is it okay for you to do that? Not really, because you can just do points on your paper. That doesn't actually work on my computer. Okay, now is this correct? Well, not quite. I need to put a 2 negative around there. Oops, 2 negative. It doesn't matter if you do 2 negative or negative 2. And then I need to count up electrons. Remember, each bar is 2 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay, so that's good. Well, what about this structure here? Might that work if I do this? And put a 2 negative around that? Well, let's count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Ugh! It does. It has enough. Now, this relies on sulfur having an expanded octet. Can sulfur have an expanded octet? It's third period, so you betcha. So this is good. What if I do the next logical one? Let's do S double bond O, double bond O, O, O. Then, oh boy, now this is just starting to get crazy. Okay, and this also has 32. All right, so here's one with all double bonds. Oh, actually, I'm going to need 3 double bonds. One with all double bonds. And again, you're not going to need this many structures, but I want to put these up here so you can see the pattern. And one triple bond, just so you can see what that does. Okay. And for the second row, what I'm going to do is I'm just going to put a 2 minus around the whole thing just to make it true. Okay. So the question then becomes, well, how do you differentiate a good structure from a bad structure? Okay, and we're going to use something called formal charge. And formal charge isn't really in your textbook, all right? So here are the steps, and I'll include this for your viewing pleasure somewhere else. So let's kind of go through this bit by bit. So draw possible Lewis structures. Check, okay? Now, once you've done a couple of these, you'll learn how to predict what you're going to need. Okay, so you can be strategic about what structures you choose, but that's kind of a little bit more of an advanced level thing. So you'll need some practice first. I would say generally start with no double bonds and work up to 2 or 3 or however many you need. Okay, assign formal charge to each using the formula formal charge equals VE minus LE minus 1/2 BE. So this VE, hopefully you could guess, is valence electrons. Okay, this is LE is electrons in lone pairs. So one thing that's important to keep in mind here is that one lone pair equals 2 for the LE, 2 lone electrons. Okay? And then minus 1/2 BE, so this is electrons in bonded pairs. Okay? So here we go. We're just going to start assigning things. VE minus LE minus 1/2 BE. Okay, so if I have an oxygen that's single bonded with its 6 valence electrons, it's always going to be the same, right? Because if it doesn't matter if it's here or if it's down here. So the good thing about this is you can eliminate a lot of stuff really quickly. Okay, so oxygen. So the formal charge here, I'm just going to write my valence electrons minus lone electrons minus 1/2 electrons in bonded pairs. Okay, so for this one, the formal charge is valence electrons. Well, oxygen has 6 minus the lone electrons, 2, 4, 6 minus 6 minus 1/2 times the bonded electrons. Well, there are 2 bonded electrons, and we want half of that, so that's really 2 over 2. So the formal charge of this is 6 minus 2 over 2, negative 1. Okay, so now anywhere that there is a single bonded oxygen, I'm going to write a little negative 1 next to it. And you can see that this actually is not as bad as it seems. Okay, so what about an oxygen that's double bonded? Okay, so the formal charge here is 6 minus 2, 4 minus 4. There are 4 electrons in these 2 bonded pairs over 2. 6 minus 4 over 2. That is 0. Okay, because this is 2. So 6 minus 4 minus 2 is 0. All right, so anywhere that there's a double bonded oxygen, we can write a 0. These are all zeros. Okay. And then that just leaves the sort of oddballs, all right? So, like, for example, the sulfur. This sulfur, the formal charge here is 6 minus 2, 4, 6, 8. There are no electrons in lone pairs, but there are 8 electrons in bonded pairs. Sorry, that's a plus 2, so that gets a plus 2. This one's going to be, formal charge is 6 minus, there are no lone pairs, minus 2, 4, 6, 8, 10. 10 electrons in bonded pairs, so that's 5. So 6 minus 5 is positive 1. Okay, here, that's 6 minus 0 minus, this will now be 2, 4, 6, 8, 10, 12. 12 over 2, so that's 6. So that's 0. So hopefully you'll see that there's a bit of a pattern here. So this is minus 1 and this is minus 2. And then let's do the two oddballs here. The formal charge for that oxygen, triple bonded oxygen, is 6 minus 2 minus 2, 4, 6, 6 over 2. So that's plus 1. Okay, and then this sulfur would be, the sulfur is 6 minus 0 minus 1, 2, 3, 2, 4, 6, 8, 10, 12. 12 over 2 is 0. Okay, so now I've assigned formal charge. So you can see right away that there are some trends, right? So one of the things to keep in mind is, let's take a look at the total charge, all of the formal charges added together in this one. So that's 0, 0, 0, minus 1, 2 minus. This is 3 minus, plus 1 is 2 minus. This is 4 minus plus 2 is 2 minus. So it should always, the formal charges on all the atoms should always add up to the charge of the ion. That's a sort of check. Okay, now we need to determine the best structure. So positive formal charge only on central atoms, no external atoms. So this one that had a positive charge out here, that was bad. Okay, so we can go ahead and say that that is awful. This one here, where we have formal charge of minus 2, that's not good because we want positive charges or zeros on central atoms. Okay, formal charges other than plus 1, 0, and minus 1 are rare. So if basically what I mean by that is charges other than plus 1, minus 1, and 0 are just not going to happen. Okay, I won't give you anything tricky like that. All right. Least number of atoms with formal charge. So a formal charge of 0 is good. So let's take a look at what's left. So we're basically trying to decide, oh, we eliminated this one because it has a plus 2. So this one has 2 atoms with a negative charge. Everything else has 0. This one has 4 atoms with charge and only 1 0. So this is our best structure. Okay? That is our best structure. And that is how you use formal charge. These are long, long, long problems, okay? I probably would only give you 1 or 2. No, sorry, 1 on a test. But this is how you do them. It's a very in-depth analysis, and I'll kind of give you little prompts along the way.